Okay, welcome back. This is part 2 of chapter 13. And this is the third topic that we're going to talk about for chapter 13. It's called Principles of Information Gathering. So we have talked about what is useful information and then how to value useful but imperfect information. Here we will introduce yet another criteria to guide your process in information gathering in a more efficient and cost-efficient way. So the 3 principles of information gathering are: first, information should be relevant. You only pay for observations for distinctions that are relevant to the distinction of interest. If an observed distinction is not relevant to the distinction of your interest, then that information is not useful or relevant at all. Second criteria is called material information. So sometimes the observation are relevant to the distinction of interest. However, it doesn't change your decision. In that scenario, you should not pay anything for the information either. And that information is called immaterial. So you only should be paying for material information that has the possibility of changing the decision that you're going to make. The third one is the information gathering should be economical, meaning you should not pay more than the value of the information. That is why we have been so interested in value perfect or imperfect information. Remember that value that we have calculated is the maximum price that you are willing to pay. Okay? If you pay some price that is lower than the maximum price, that makes you indifferent, then that is economical, meaning you're incurring some surplus by paying a lower price. If the price for that information is higher than your willingness to pay, then you should not pay for that information. That is, the cost exceeds the benefit. So we'll take a closer look at the second principle in this part of the lecture for chapter 13, material information. So material information is the information that can potentially change the course of your action. So again, if we look at Kim's party problem, okay, so what we've known already is that given Kim's information or prior knowledge about the weather, that 40% is likely a sunny day and 60% likely it is a rainy day. Given that probability, Kim would choose indoor. Okay. Now the question is, what kind of probability? What kind of a probability on sunny or rainy would change Kim's decision to a porch party or even to an outdoor party? Okay, so that is the question we're trying to answer on this slide. So as it turns out, what we're seeing on this graph is that we are using P, which is a number between 0 and 1, to represent the probability of a sunny day. And then 1 minus P is just the probability of a rainy day. Okay, so we're being agnostic about what the value of P is. We're just set it to be a constant number that we may change from one to another. Now, the choice between outdoor, porch, or indoor is essentially a choice between this deal, and this deal. Again, the P's in the 3 deals are the same, which is again because the choice of party location doesn't change the probability of the weather being sunny or rainy. Okay, so what we want to know is what kind of P will lead Kim to choose this option. What kind of P will lead Kim to choose this option? And what kind of P will lead Kim to choose this option? In order to do that, we need to figure out what is the U value of this uncertain deal for P. What is the U value of this uncertain deal for P? And what is the U value of this uncertain deal for P? Okay. And the way to do that is just going through the formula, apply the formula to find the U value of an uncertain deal. So over here, the U value of this uncertain deal would be, write something for you. That would be P times 1 plus 1 minus P times 0. Okay, again, this number 1 is the U value of $100 or the U value of an outdoor party in the sun. And this 0 is the U value of an outdoor party in the rain, which is 0. Okay, and to simplify this expression, the U value of an outdoor party would be equal to P. Okay. And next, the U value of a porch party is essentially equal to P times 0.950 plus 1 minus P times 0.323. Okay, here, this is the probability of a sunny day times the U value of the prospect of a porch party in the sun, which is over here. Again, these U values are found by looking at Kim's U curve or by looking at Kim's U function. And 1 minus P is the probability of rainy day. 0.323 is the U value of a porch party in the rain, which is worth $20. And simplify this one, you will get an expression like this. Okay, I'm omitting the middle process. If you're interested, you can do that yourself. Okay, and then using the same method, you can do this one. So this U value would be equal to P times 0.568 plus 1 minus P times 0.667. And simplify that expression, the U value of an indoor party given any P is equal to this. Okay, now is the time to decide what P would lead Kim to choose this one, what P would lead Kim to choose this one, and what would P lead Kim to choose this indoor option. As it turns out, you can compare this one with this one with this one. Turns out if P, the probability of sunny day, is less than 0.47, then the U value here would be the highest of the three. Okay. If the probability of sunny day is between 0.47 and 0.87, then this value will be the highest. That means Kim would choose porch party instead. And if P is greater than 0.87, then this will be highest, and Kim would choose outdoor. These threshold values, we got this by comparing the three U values. Okay. Again, the process is omitted. You can just take it as is. If you are interested, you can just do some comparisons between P and 0.323 plus 0.627 times P, and between those two and this number. Okay, and solve for P. For multiple inequalities, you will get this range as stated on this slide. So for Kim and for Kim's party problem, 0.47 and 0.87 are the break points where information could be material. Okay. So again, recall that without the additional information, Kim would choose indoor. If Kim receives some kind of a message from any kind of a detector, that may lead to a P that is no longer less than 0.47, then that information has the potential to change Kim's decision. So this is just a quick preview of what we're going to do next. Again, we're looking at a special type of ring detector with an accuracy called P. Okay, again, this P is different from this previous P. The P on this slide is not necessarily is not the same P on this slide. We're just using P as a temporary unknown and solve for that. The P on this slide is not the same with the P on this slide. On this slide, we're using P to refer to the accuracy of a ring detector. And as you can see, we have analyzed the situation or a ring detector with P equal to 0.8. And just similarly, you can analyze this inferential form and assessed form with P equal to 0.9, 0.7. And when P is equal to 1, we're looking at clairvoyance. Okay, so when P is equal to 1, this and this will be equal to 1. Okay. This is equal to 1, meaning the probability that the weather is going to be sunny given a rainy day message is 0. Okay, again here we're now focusing on these two probabilities rather than these two likelihood probabilities. So as it turned out, if the information is provided by clairvoyance, then Kim would choose outdoors if the message from clairvoyant is sunny. Because if the message of the clairvoyant is sunny, then the likelihood that the posterior that the weather is sunny will be 100%, which is beyond the point. Since 1 is greater than 0.87, then Kim would choose outdoors. Okay, and when P is equal to 0.8, we're looking at Acme ring detector that we have looked before. Then, if the message from the Acme ring detector is sunny day, then the probability that the weather is actually going to be sunny is 0.727. So when the probability of sunny day is 0.727 from previous slide, we know it is between 0.47 and 0.87. That means when a ring detector tells Kim that the message is sunny, then Kim would select porch. Okay, so what are we trying to look at? Over here, the ring detector and the clairvoyance both has the potential to change Kim's decision to either outdoor or porch if the message is sunny. If the message is rainy, of course, Kim would still choose the indoor party. However, on the other hand, if the message is sunny, then Kim would change her choice of location to outdoor or porch. When the accuracy of the ring detector is 0.5, then that detector is irrelevant to the probability of the weather, Then it doesn't, Kim's probability assignment to the day being sunny is not affected by the ring detector's message, and Kim's decision is not affected. Kim would always choose indoor. So this coin flip, this detector that is in the same spirit of a coin slip is not useful or material. I want to say that the worst detector is the kind of detector that has an accuracy of 0.5. 0.5 means it is randomly sending out a message of raining or sunny. Okay? The kind of detector that has an accuracy of 0 is actually very useful. What does that mean? P is equal to 0, meaning when the weather is sunny, the detector would predict it is going to be rainy day with 100% of the chance. When the weather is rainy day, then the rain detector would predict it's a sunny day with 100% of the chance. It is predicting exactly the opposite of the weather. So then going from this assessed form to the inferential form, then this probability would be 1, meaning if the message is sunny day, then you just flip the message and predict that the weather is going to be a rainy day for sure. If the message is a rainy day, then you would interpret that message as the day is going to be a sunny day for sure. So P equal to 0 is almost as good as P equal to 1. Okay, what I'm trying to say is this assessed form, we can do this assessed form for P in a lot of, for a lot of values of P in the range between 0 and 1. And then for each P, we can reverse the tree to get the inferential form, okay? And then after we do that, we can sort of graph what this probability with this P, okay? So again, here, what I'm going to do is I'm going to change the P from 0 to 1. And then what we're interested to know is this probability, okay? So I'm going to put the P over here onto a horizontal axis. And I'm going to put this probability to the vertical axis. Okay, so when P is equal to 1, this is equal to 1. When P is equal to 0.8, this is equal to 0.727. You can figure it out by yourself. When P is equal to 0.9, this would be another number. When P is equal to 0.6, this will be another number. So there is this pairwise relationship between the accuracy and the probability of the day being sunny when the message is sunny. And then we can graph that a lot of findings, series of findings like that in this graph, which I call a crazy graph. So here, the horizontal axis represent this P, this accuracy. And this vertical axis represent the posterior probability of sunshine. And what we're going to draw is the posterior probability of sunshine when the message is sunny. Okay, so what we're going to graph first is this probability. When the message is sunny, what is the posterior probability that the day is going to be a sunny day? And we've already calculated for P equal to 1, that probability is equal to 1. So we find that point. So when P is equal to 1, go up, and the probability, the posterior probability is 1. So 1 over here. So that corresponds to this point. Okay. When P is equal to 1, the posterior probability is equal to 1 over here. And we've also done this for P equal to 0.8, then the posterior belief or probability is 72.7%. So that would correspond to the point over here. So you can say, if you go down, that would be 0.8. If you go left, this would be 0.727. This would be 0.8. Okay, so this point over here represent the fact that when the accuracy of the detector is 0.8, the posterior probability of sunny day given a sunny day message is 72.7%. Okay, and also when P is equal to 0.5, there's no information, no extra information at all. The probability of a sunny day given a sunny day message is not changed from your prior belief. This information does not provide any additional information. Your posterior belief about the day being sunny is equal to your prior belief that the day is sunny. So that corresponds to this black dot over here. Okay, again, here, this is 0.4. This black dot represent the fact that when the detector's accuracy is 0.5, then the probability of the day being sunny day given a sunny day message is just the prior belief, which is 0.4. Okay, we did these three, and you can do another one over here. Let's suppose when P is equal to 0.9, it is somewhere over here. When P is equal to 0.7, it is somewhere over here. You do a lot of calculations, and then what you will be able to do is to connect all these dots with a curve. Okay, so that is this curve over here. This curve represents the relationship between accuracies of detectors and the posterior probability of sunshine when you read a message from that detector. Okay, so again, this graph represents this probability. This probability is the posterior probability of sunny day given a sunny day message. So that's what this dark gray curve is about. As a matter of fact, we can now use this curve to figure out what kind of accuracy will have the potential to change Kim's decision when that detector gives a message of a sunny day. So we have already established when the probability of sunny day is below 0.47, that means when the vertical axis is in this range, okay, then if Kim receives a sunny day message, that will not change her decision at all. So when the posterior belief is in this range, Kim would still choose indoor. And when the posterior belief is in this range, Kim would change her decision to porch. And when the posterior belief is in this range, Kim would change her decision to be outdoor. Then the question is, these posterior beliefs, what kind of accuracy do they correspond to? Okay, so what we can do is to give a horizontal line. So for 0.47, so, and then write down, that is 0.57. So this number here is 0.57. That means if a rain detector has an accuracy that is above 0.57, which means we're looking at the rain detector in this range, then those kind of rain detector will change Kim's posterior belief to this range if the message is sunny. And in this range, these two combined, Kim will change her decision from indoor to porch or outdoor. So here it's outdoor, here it's indoor. I'm sorry, it's not indoor, it's porch. Okay. And then if the detector's accuracy is in this range, suppose we have a ring detector that has an accuracy at this point. Use another color here. If a ring detector has an accuracy like 0.52, then when that detector tells Kim that the day is going to be sunny, then that corresponds to a posterior belief that is roughly between 0.4 and 0.47. So when this detector gives a sunny day message, this will be Kim's belief that it is going to be a sunny day, and it is below this threshold. So even given a sunny day message, Kim would still choose indoor. So a rain detector with this accuracy will not change Kim's decision after sending Kim a sunny day message, which means the information provided by this detector is immaterial. So any rain detector that has an accuracy in this range can potentially change Kim's decision if the message from the detector is the day is going to be sunny. And again, p equal to 5 is absolutely useless. So as you can see, when the rain detector's accuracy is in this range, things will be interesting. Over here, when detector's accuracy is 0, it's meaning it will get the weather absolutely wrong or to the opposite. Then a lot of information can be deducted from that kind of a detector. So that's why we're also interested to know the posterior probability of a rainy day when the message is rain. Okay, so as we can see before, when the accuracy is equal to 0, means detector will get the weather to the opposite perfectly. That means when the message is rainy day, the weather is actually going to be sunny. So that corresponds to this point, okay? Again, this vertical axis represent the posterior probability of sunshine or of a sunny day. But now we're looking at the posterior probability of a sunny day given a rainy day message. What we've seen before in this dark curve, in this curve, is the posterior of sunny day when the message is sunny. What we're going to see now is the posterior probability of sunshine given the message is rainy day. It is sometimes very useful to look at this probability too, just like what I illustrated over here. When the accuracy is 100% opposite to the weather, of course you can infer the weather from that detector. And when p is equal to 0.2, which means when it is going to be a sunny day, the rain detector will predict it's a sunny day with 20% of the chance. And the rain detector will predict it's a rainy day with 80% of the chance. And the probability of a sunny day given a rainy day message is now 0.727, correspond to this point. Okay, when p is equal to 0.2, the probability of sunshine is 0.727, giving a rainy day message. And then 0.5 is still no information at all. So again, we can get a lot of probabilities like this and then connect them with a line. So what this line means is the probability of the day being sunny when the message is rainy. Okay, so here, this is the always opposite detector. Here is the always accurate detector. Okay. So as it turns out, when a detector has a range, when the detector has an accuracy, let's say 0.3, then when the detector gives you a message, so here, detector's accuracy is 0.3, and when the message is sunny, then you would predict the probability of sunny day is only a little over 0.2. However, when that 0.3 accuracy rain detector gives you a message of a rainy day, then you would believe that the weather is going to be sunny with 0.67 of a probability. So when you do get a rainy day message from a rain detector that has 30% of accuracy, you would deduct that the weather is going to be sunny with 67% of the chance, which will change Kim's decision to have the party on the porch. So a rain detector with 0.3 accuracy can potentially change Kim's decision to a porch party when it sends out a message that the day is going to be rainy. It's like telling the opposite, okay? So that is why a detector with accuracy of 0.3 can also give material information. When we say material information, we're saying that messages that you get from the detector can potentially change your decision. We didn't say that it has to be the sanity message that change your decision. It could also be that a rainy day message that is changing your decision too, which is the example over here. When accuracy is 0.3, posterior belief of a sunny day given a rainy day message will actually be very high, which will change Kim's decision to a porch party, which is useful and material information since it changes Kim's decision from indoor to porch when the message is rainy. Any detector in this range will work like that, okay? Any detector with an accuracy between 0 and this value will change Kim's decision to either porch or outdoor when the message turned out to be raining. So, as it turns out, detectors with accuracy in this range is absolutely not useless, but provides absolutely immaterial information, because no matter what the message is, Kim would always choose indoor. For example, suppose you're looking at a rain detector with an accuracy over here. Okay, then you would go up. When you are here, go over here. That represents when a rain detector with the accuracy of 0.47, this is 0.47, then if the message is sunny, Kim's belief that the day is sunny will be changed to 0.38, which is still below 0.47, the threshold, which means Kim would choose indoor if the message is sunny. Now, what if the message is rainy? Then we should go to this curve. So if the accuracy is over here and the message is rainy, then the posterior belief that the day is going to be sunny is over here, which is still below this threshold at which Kim would switch her choice from indoor to porch. Okay, so an accuracy in this of here, 0.47, will not change Kim's decision to porch or outdoor, no matter what message that detector sends. Okay, so that is why any point over here will have that effect, meaning any point, any accuracy in the range between 0.47, I think, or 0.43 actually, and 0.57 will not change Kim's decision no matter what kind of a message it sends. So the information provided by a rain detector with an accuracy between 0.43 and 0.57 provides immaterial information. Those detectors are immaterial detectors for Kim when we're looking at the party problem. Okay. I want to say that the usefulness or the material or immaterial of a detector is decision specific. So as you recall, we find out this threshold 0.47 and this threshold 0.87. We find these two values over here by looking at a specific decision problem over here. Okay, so as you can say, if Kim's value is not these numbers, if we're looking at another person who values these parties differently than Kim, then these threshold values will be different from these numbers. Okay, so again, material or not, detectors are material or not, it is dependent on who you are looking at, what decision you are looking at, and what prior, these priors also matter as well. Okay, so this is the end of the lecture for chapter 13. I hope you can sort of look at, this is a very, very tricky part of this chapter. But the logic or intuition is pretty clear, and we're just looking at what kind of accuracy do we need for a rain detector in order for it to be able to potentially change Kim's decision. And the answer is any rain detector with this range will change Kim's decision to either a porch party or an outdoor party if the message is rainy day. Any rain detector in this range, Kim would change her decision to porch or outdoor if the message is sunny. Any accuracy in this range, Kim will never change her decision, no matter if it's a rainy day message or a sunny day message. Okay, immaterial information over here, material information. Okay, so this is the end